Dr. Luna is a senior researcher and lecturer at Safari Research Group at ETH Zurich. He received the Bachelor in Science and Master in Science degrees in Telecommunication Engineering from University of Sevilla, Spain in 2001, and the PhD degree in Computer Engineering from the University of Cordoba, Spain in 2012. Between 2005 and 2017, he was a faculty member of the University of Cordoba. His research interests focus on processing in memory, memory systems, heterogeneous computing, and hardware and software acceleration of medical imaging and bioinformatics. He is the lead author of PRIM, the first publicly available benchmark suite for a real-world processing in memory architecture. I guess now you can start. Thank you.
Yeah, thank you very much, Ahmad, for the invitation and for the kind introduction. I hope you can see my slides and also hear me well. I would like to start this presentation by thanking my co-authors, Izzat, Ivan, Cristina, Geraldo, and Professor Onur Mutlu. Today, what I'm going to do is introducing this work titled Benchmarking Memory-Centric Computing Systems, Analysis of Real Processing in Memory Hardware. Let's start with some brief executive summary. We know that data movement is a major bottleneck in current computing systems. The data movement between the memory and storage units and the compute units of current computing systems consumes a lot of execution cycles and energy. Processing in memory is a paradigm that can tackle this data movement bottleneck, also called von Neumann bottleneck or memory wall. And although this has been proposed for more than 50 years, technology challenges prevented from the successful materialization of PIM. That happened until 2019, where a French startup, UPMEM, designed and fabricated the first publicly available real-world processing in memory architecture, which consists of DDR4 chips that contain some small in-order cores called DRAM processing units or DPUs. In our work, we provide an introduction to the UPMEM programming model and PIM architecture, a micro-benchmark-based characterization of the DPUs, and a benchmarking and workload suitability study. Our main contributions are a comprehensive characterization and analysis of the first processing in memory architecture, a benchmark suite, PRIM, which is the first benchmark suite for a real-world processing in memory architecture. PRIM contains 16 benchmarks that we have characterized using strong and weak scaling experiments. And we have compared the performance on the UPMEM-based PIM system to the state-of-the-art CPU and GPU counterparts. Key takeaways of our work are workload characteristics for PIM suitability, programming recommendations, suggestions, and hints for hardware and architecture designers of future PIM systems, and the PRIM benchmark suite, which can be used as programming samples for processing in memory systems and for evaluation and comparison of current and future PIM systems. Let's start with a little bit of motivation. Data movement is it's dominating performance and energy consumption in current computing systems. For example, recent studies showed that the energy consumed by data movement accounts for 62% of the total system energy in consumer applications, 42% in scientific applications, and 35% in mobile applications. If we take a look at that current system on chip, we will find different devices like CPUs and GPUs. We have a cache hierarchy, we have accelerators, and among all these components and the main memory or the DRAM, there is a lot of data movement, and this data movement is both dominating the compute system. For this reason, we believe that compute systems should be more data-centric, and processing in memory is a way of doing this by placing compute units where the data resides, which is in memory or in the storage. So as I said before, the first real-world processing in memory architecture was released by UpMem, this French startup, in 2019, and it essentially consists of standard DIMMs of the DDR4 DRAM memory, where there are a number of chips called PIM chips, typically 8 or 16. And inside each of these PIM chips, there are several, actually 8 DRAM subarrays and DRAM banks, and connected to them 8 DRAM processing units or DPUs. Let's start with one key takeaway of our work that shows how PIM can alleviate the shortcomings of processor-centric systems. We show in our work that UpMem-based PIM systems outperform state-of-the-art CPUs in terms of performance by more than 20 times for the 16 PRIM benchmarks on average, and they also provide very good improvement in terms of energy efficiency. And when compared to state-of-the-art GPUs, we observe that for a majority of our PRIM benchmarks, the larger UpMem-based PIM system that we have used also outperforms a GPU, a recent Volta GPU, by 2.54 times. So in the end, or the key takeaway here is that UpMem-based PIM systems are more energy efficient for CPUs and GPUs on the workloads that they provide performance improvements. And the reason for this is that both the energy savings and the performance improvements are coming from the reduced data movement that an UpMem-based PIM system, or a PIM system in general, can provide with respect to CPUs and GPUs. Many of the details of this talk are in the paper that we submitted to this CUT workshop, and also in the longer version that is already publicly available at arXiv. Over the course of this presentation and the papers, you will find different colored boxes that provide some general programming recommendations that stem from our work, key observations, and key takeaways. Okay, let's start with an overview of an UpMem-based PIM system. So the integration of the UpMem DIMMs in a system follows what we call the accelerator model, where the UpMem DIMMs can be seen as a loosely coupled accelerator or coprocessor. This means that we need to explicitly move data from the main memory of the host processor and the memory of the accelerator. And also we need to explicitly launch the kernel, which is the function that runs on the UpMem DPUs, on the UpMem processors. This in some way resembles GPU computing, but it's different because the host CPU accesses the UpMem DIMMs directly using the memory bus, while in the GPU computing paradigm, what we typically have to do is transferring data back and forth over a PCI Express bus or NVLink. Okay, so regarding the system organization, we will find that in an UpMem-based PIM system, UpMem DIMMs, which are these PIM-enabled memory, coexist with regular DRAM DIMMs, which represent the main memory of the host CPU. If we take a closer look, we will see that on each UpMem DIMM, there are 8 or 16 chips. This means 1 or 2 ranks of 8 chips each. And inside each PIM chip, we find 8 64 megabyte DRAM banks called MRAM or main RAM, and 8 DRAM processing units. So in total, in one rank, we have 64 of these DPUs. This is a pictorial representation of one of the UpMem-based PIM systems that we have used in our study. In particular, this one contains 20 PIM DIMMs, which is 40 ranks, and it's a dual socket x86 machine that has access to more than 2,560 DPUs and a total of 160 gigabytes of PIM-enabled memory. This is a picture of this system where we can identify the 2 CPUs. We also see some DRAM DIMMs, which are the main memory, and then we also have some PIM-enabled memory, the UpMem DIMMs. And this is another smaller UPMEM-based PIM system that contains 640 DPUs and 40 gigabytes of PIM-enabled memory. And we have also used this one in our study. Okay, let's just start with a few concepts about how to program this system. The first first programming example is vector addition, which is one of our benchmarks. In vector addition, as you know, what we do is performing or calculating the element-wise addition of two arrays, A and B, and storing the output in an array C. The way that we partition this computation across the DPUs is by first dividing the arrays, input and output arrays, into different chunks that are assigned to the different DPUs. And then inside each of the DPUs, we use tasklets or software threads that run on the DPU, and each of them receive a chunk of data out of the data that was assigned to each of the individual DPUs. So you can see here how we distribute this computation over different number of DPUs and tasklets. So as I said before, in the accelerator model, we need to transfer data from the main memory of the host CPU to the PIM-enabled memory. So that's why the UPMEM SDK provides some APIs to perform these transfers. So there are what we call CPU-DPU transfers and DPU-CPU transfers. And there are different ways of performing these transfers. One way is using a serial API that targets a single DPU and a single MRAM bank. And then, or we can also use parallel CPU-DPU or DPU-CPU transfers where we target multiple DPUs and multiple MRAM banks. And then there are also broadcast CPU-DPU transfers when we target multiple DPUs, but we transfer a single buffer to all DPUs. It's important to understand what's the performance, and we will see quickly the performance of these CPU, DPU, and DPU, CPU transfers, because there's no direct communication channel between DPUs. And this means that the inter-DPU communication takes place via the host CPU using both CPU, DPU, and DPU, CPU transfers. In our PRIM benchmark suite, we provide different communication patterns. For example, merging of partial results to obtain a final result. This computation will be done on the host CPU and requires only DPU to CPU transfers. And also another pattern is the redistribution of intermediate results for further computation. In this case, we need transfers in both directions. So how fast are these transfers? We have characterized how fast these transfers are by using two sets of experiments. In the first one, we are using a single DPU, and what we do is that we vary the data transfer size from 8 bytes to 32 megabytes. Here in this plot, you can see the sustained CPU, DPU, and DPU, CPU bandwidth for different transfer sizes. This is CPU to DPU, and this is DPU to CPU. So one key observation here is that larger CPU, DPU, and DPU, CPU transfers between the host main memory and the MRAM of the DPUs in the UPMEM DINs result in higher sustained bandwidth. We have also performed some experiments using one run where we vary the number of DPUs from 1 to 64. And here you can see the results for serial transfers. We see that the bandwidth is flat because we are targeting the different DPUs in a serial manner. And this is the performance or the sustained bandwidth for the parallel transfers. So the key observation here is that the sustained bandwidth of parallel CPU, DPU, and DPU, CPU transfers, and also the broadcast transfers, increases with the number of DRAM processing units inside a bank, as you can see in this plot. Now we are going to talk briefly about the internals of the DRAM processing units, and then we are going to characterize their behavior. We are going to essentially measure what are their arithmetic throughput and bandwidth limits. So this is how the UPMEM-based PIM system looks. Recall CPU, host CPU, main memory, PIM-enabled memory, composed by multiple PIM chips. And we can take a closer look at this PIM chip. So here we will find a DDR4 interface for the host to read and write from the MRAM banks. And then we have a control status interface for the host to send commands to the DPU, to the pipeline of the DPU. We also see 8 of these 64 megabytes DRAM banks, which are called the MRAM, and a DMA engine to access these banks, actually one DMA engine per bank. And then there are also, for each DPU, there are two SRAM-based memories. One of them is for instructions, and the other one is a scratchpad memory for input and output operands that can be directly accessed from the DPU pipeline. This DPU pipeline is an in-order pipeline. Today, it runs at a frequency of up to 350 megahertz. It's a fine-grained multi-thread pipeline that can use up to 24 hardware threads, and it contains 14 pipeline stages, as you can see on the screen. Yeah, as I said, we created micro benchmarks to measure what's the arithmetic throughput that these DPUs can achieve. So here I'm going to show you some results for one single DPU. What we do is that we stream over an array in WRAM. So we allocate an array in WRAM, the scratchpad SRAM-based memory, and perform read, modify, write operations. We change the number of tasklets from 1 to 24, which is the maximum number of hardware threads, and then we perform different versions with different arithmetic operations like add, subtract, multiply, and divide, and different data types, 32 and 64 integers, floating point, and double precision. So these are some results you can see on the y-axis, the arithmetic throughput. On the x-axis, we have the number of tasklets from 1 to 24, and these are results for different data types on one DPU. These are addition and subtraction for integer 32. This is multiplication and division, and these are the results for other data types. So one key observation from these four plots is that the arithmetic throughput of a DRAM processing unit saturates at 11 or more tasklets, and this observation is consistent across data types and operations. Another observation is that there is a huge throughput difference between addition and subtraction of integers and the rest of operations. And the reason for that is that the DPUs have native support for 32 and 64-bit integer and integer addition and subtraction, but they don't have native support for multiplication and division or for floating point operations. So these operations are emulated by the UpMem runtime library, and this leads to much lower throughput, as we can see on this plot. Okay, in the paper, you can also find more results and more insights about the previous experiments. Here, also recommend you to check the paper if you are interested about what's the access, how we access from the DPU pipeline to the WRAM, and what's the bandwidth that we can achieve. But now we are going to take a closer look at the access to the MRAM bank, to the 64 megabyte DRAM that each DPU is coupled with. So yeah, here we are. So we are going to measure essentially the transfers between this MRAM bank and the WRAM. Okay, so we performed different experiments to measure the bandwidth and the latency, different micro benchmarks. In the first one, we are going to measure the latency of a single DMA transfer. Then we also have the different versions of the stream benchmark to measure the streaming bandwidth, and we also have bandwidth. We also have micro benchmarks for strided access patterns and random access patterns. So let's start with the latency measurements. So here we measured the bandwidth and the latency of different data transfer sizes between MRAM and WRAM. We changed the size from 8 bytes to 2 kilobytes. We obtained the bandwidth using this expression after measuring the latency of each of these transfers here. And one important observation is that we noticed that the MRAM latency can be modeled with a linear expression, something like this, where we have a fixed cost alpha and a variable cost beta times size. So as you can see, our linear expression or model matches perfectly well our measurements on the real system. And one thing that we infer from our measurements and from this linear model is that beta equals 0.5 bytes per cycle. So this means that the theoretical maximum MRAM bandwidth is 700 megabytes per second per DPU. Imagine in a system where you can have more than 2000 DPUs. So key observation is that the access latency to the MRAM bank increases linearly with the transfer size, as we have shown with this expression here, and also that the maximum theoretical MRAM bandwidth is 2 bytes per cycle. We also, as I said, implemented the different versions of the stream benchmark, and actually we have 2 different versions for the copy benchmark. So in the slide, you can see the sustained bandwidth for the different versions of the stream benchmark for different number of tasklets. So one first observation here is that for some of these versions, the bandwidth saturates at a number of tasklets that it's smaller than 11. And this is what we call a memory-bound workload. The reason is that here, the latency of accesses to the MRAM bank takes longer than the latency of the execution of arithmetic operations or WRAM accesses in the pipeline. But for other other versions of the streaming benchmark, like Scale and Triad, the pipeline latency is larger than the MRAM access latency. So the performance saturates at 11 tasklets. And this is what we call a compute-bound workload. In the paper, you can also find results for strided access patterns and random access pattern. So now we are going to take a look at something else. Is how the arithmetic throughput changes when we change the operational intensity. So here we are going to relate the latency of access to the MRAM, moving data between MRAM and WRAM, and the execution of arithmetic instructions and accesses to WRAM in the pipeline. So in these experiments, we are going to characterize what are the memory bound and the compute bound regions of the DPU for different data types and operations. And essentially what we do is that we move a chunk of data from MRAM to WRAM, then we iterate over the elements of this array in WRAM and perform a variable number of operations on the data, and we write back to the MRAM. This experiment resembles the roofline model, right, where we obtain the compute throughput of a system with respect to the arithmetic intensity or operational intensity. And here we define the operational intensity as the number of arithmetic operations performed per byte accessed from MRAM. So some important observations from our experiments is that there is a memory bound region where the arithmetic throughput increases with the operational intensity. Here on the y-axis, you can see the arithmetic throughput. On the x-axis, the operational intensity from very low value. This area here is the memory bound region for different number of tasklets. As you can see, all these dots represent different tasklets from 1 to 16. And then there is a compute bound region where the arithmetic throughput is flat at its maximum for the different number of tasklets. We define the throughput saturation point as the operational intensity where the transition between the memory bound region and the compute bound region happens. And one important observation in this plot is that the throughput saturation point is as low as 0.25 operations per byte. That is 1 integer addition per 32-bit element fetch from the MRAM. And this trend is very similar for other data types and operations, or even worse. So we see that the throughput saturation point happens at low or very low operational intensity, which means that the DPU is fundamentally a compute-bound processor. So we expect that most real-world workloads will be compute-bound when implemented on this PIM architecture. So now let's take a look. Let's talk about our PRIM benchmarks. So our goal is to create a common set of workloads that can be used for different purposes, like evaluating the PIM architecture, comparing software improvements and compilers, and compare future PIM architectures and hardware. And we have 2 key selection criteria. We select workloads from different application domains, and these workloads are memory-bound on processor-centric systems, on CPUs and GPUs. In total, we have 16 benchmarks for 14 different workloads. And these are, so the different benchmarks and the application domains. As you can see, we have sparse and dense linear algebra, databases, data analytics, graph processing, neural networks, bioinformatics, etc. And if we take a look at the roofline model for these workloads on a conventional CPU, we will see that all the 14 workloads fall in the memory bound area of the roofline. So in principle, they can benefit from processing in memory. We will see whether they really benefit from the UPMEM-based PIM system. These benchmarks are also diverse in terms of memory access patterns, computation patterns, and communication or synchronization patterns, both intra-DPU and inter-DPU. Okay, let's go to the evaluation. We evaluate the 16 PRIM benchmarks on 2 UPMEM-based PIM systems of different sizes. We perform strong and weak scaling experiments on 1 DPU, 1 rank, and up to 32 ranks. And we also compare the performance of 4 benchmarks on the UPMEM-based PIM systems to the state-of-the-art CPU and GPU counterparts. So these are the results for strong scaling experiments on 1 DPU, where we changed the number of tasklets from 1 to 16, and we show the execution time breakdown for the DPU time for different number of tasklets, the inter-DPU synchronization time for those benchmarks where we need to have inter-DPU synchronization. Then we have CPU-DPU transfer time, DPU-CPU transfer time, and finally the speed up over 1 tasklet for the execution of the DPU kernel. So some observations here are that in most of the cases, the best performing number of tasklets is 16. This relates to the fact that the saturation of the arithmetic throughput of the DPU usually happens at 11 tasklets, and this is consistent across most of the benchmarks. There are some of the benchmarks that don't use intra-DPU synchronization primitives. In other cases, the synchronization is very lightweight, so we don't see that the scaling is affected by the synchronization, intra-DPU synchronization that is needed. But there are also other benchmarks, these 3 in particular, where there is quite a bit of contention because they are using mutexes to access shared data structures. We can check one of these benchmarks and analyze it more in detail, one of the versions of histogram calculation that we have in our benchmark suite. Here in this version, we have a single histogram per DPU, which means that all tasklets running on the DPU need to use a mutex when we want to access to update the histogram, to vote in a histogram DIM. And this results in scaling changing when we go from 8 to 16 tasklets, and we see that the best performance is obtained by 8 tasklets. And the reason is that the use of the mutexes creates a lot of contention when updating the histogram, and this makes that the performance of 16 tasklets is worse than for 8 tasklets. These are results for 1 rank, strong scaling experiments on 1 rank, on up to 32 ranks, and also weak scaling experiments on 1 rank. You can find in the paper all the details about these experiments with a bunch of insights and key observations. So let's finalize this evaluation section with the comparison to CPU and GPU. So we identify some workloads that are more PIM suitable, some of our PIM benchmarks, others are less PIM suitable, and here you can see the Genome values. So some key observations are that both processing in memory systems outperform the CPU for all benchmarks except 3 of them. And as you can see, the speedups are quite impressive. We are almost in 2 orders of magnitude performance improvement for the larger UPMEM-based PIM system. We identified that some of the benchmarks are more PIM suitable because they compare better to the GPU. And actually these 10 PRIM benchmarks out of 16 outperform the GPU by an average of 2.54 times. And also for the smaller UPMEM-based PIM system, the performance of these benchmarks is comparable to the performance of the GPU. So key observation here are the 3 key characteristics of these 10 benchmarks. They have streaming memory accesses, they have no or little inter-DPU synchronization, and they have no or little use of integer multiplication, integer division, or floating point operations. So these three key characteristics make a workload potentially suitable for the UPMEM-based PIM system. Now we can also check the energy comparison. Here we could only compare to the smaller processing in memory system, because for the larger one, the energy measurement was not available. But we see that there are also very nice improvements in terms of energy savings for the UPMEM-based PIM system with respect to the CPU. So some key takeaways to wrap up. The first key takeaway is that the throughput saturation point of the DPUs is pretty low. So the UPMEM PIM architecture is fundamentally compute bound. So as a result, we expect that most suitable workloads are memory bound on processor-centric systems, on conventional processor-centric systems. Second key takeaway is that the most well-suited workloads for the UPMEM PIM architecture use no arithmetic operations or use only simple operations, such as bitwise operations and integer addition and subtraction. Also, the most well-suited workloads for the UPMEM PIM system require little or no communication across DPUs, inter-DPU communication. In our paper, we show that this inter-DPU communication in general entails a significant overhead for most of the workloads. And finally, key takeaway number 4, the UPMEM-based PIM system outperforms CPU in terms of performance and energy efficiency on most PRIM benchmarks. They also outperform GPUs in a majority of PRIM benchmarks, those that have these 3 characteristics that I mentioned before, and the outlook is even more positive for future PIM systems, and they are more energy efficient than state-of-the-art CPU and GPUs on the workloads that they provide performance improvements. The executive summary is, the conclusion is again the executive summary that I showed in the beginning. The data movement is the main bottleneck in current computing systems. Processing in memory can alleviate this bottleneck, and finally, one company has fabricated and commercializes a real-world processing in memory architecture. This company is UPMEM. Our work provides an introduction to the programming model and the processing in memory architecture, a characterization of the DPU, a workload, and benchmarking and workload suitability study. And our main contributions are the characterization, the PRIM benchmarks, and the key takeaways of our work are the workload characteristics for PIM suitability, programming recommendations, suggestions on architecture designers, and the PRIM benchmark suite. If you want to learn more about this work, you can check our long paper, and that is already public in archive. You can also access all our codes in our public repository, and you can also watch this longer talk that I gave in July. By the way, we also teach about processing in memory in one of our courses, where we give every week some short lectures to our students. We live stream these lectures, by the way, and our students also work on their own hands-on projects. And also some interesting lectures about processing in memory are taught by Professor Mutlu in his graduate computer architecture course. So this is all from my side, and I'm glad to answer any questions.
Thank you. Any questions or comments for Juan back there? Juan. So if I am not mistaken, you said that, based on your architecture, DPU, CPU, and CPU, DPU transfers cannot happen at the same time. They are sharing the same bus, correct?
Yeah, they're sharing the same bus, so they can. In the end, they are implemented using regular memory accesses from the host CPU, right? So they can exploit memory level parallelism in a similar way as conventional memory accesses to the off-chip DRAM.
And for most of the applications that you had, it is not going to improve. But if you go page 54, I saw for some of the examples that you had, actually, if we can have a separate buses for these two, it can improve the performance a lot. 54.
Mm-hmm. Yeah, 54.
Yeah,
sorry.
so no, the next, I guess some of them here, for example, UNI, you see that the transfer between CPU, DPU actually is the majority part of the execution, right? So
Yeah, that's certainly true. And as you can see, it's not only that one. I mean, in that one specifically, one key problem that we have is that the DPU, CPU transfers cannot be parallelized because it's a unique operation. So when we partition the whole array into multiple pieces that are assigned to the different DPUs, each of the DPUs will return different sizes for the corresponding chunks, right? And that's why we cannot parallelize the DPU CPU transfers. In other cases, you can see, for example, in vector addition, how we are using parallel transfers for in both directions, and you can see how the time for these transfers reduces with the number of DPUs. But yeah, in summary, yeah, of course, there is a drawback here or a bottleneck here, that is the fact that we need to copy the data. In that sense, I don't think that that's a major issue for several reasons. The first reason is that this also affects other types of accelerators, for example, GPUs. And the second reason is that you usually don't use a GPU or an accelerator as the PIM architecture for just performing a vector addition, right? So you will normally try to offload much more computation so that it pays off to do these data transfers and also launch the kernel itself, right? Starting the execution on the accelerator, either a GPU or a PIM-based system. So that's, let's say, it's one issue right now in current systems. I think that it's a relatively small issue because this cost of the data transfers can be amortized, but also we should expect new PIM systems in the short term where the PIM-enabled memory completely replaces DRAM, right? And in that case, we won't need anymore to copy data from the main memory to the PIM-enabled memory, because all the main memory can be PIM-enabled memory. So even if the CPU has to operate later on the data, can directly access from the PIM-enabled memory without having to copy it back to the main RAM.
See. Thank you. Again, it's a very interesting work to demystify the performance of what was that, UPMEM, and it is very interesting. Okay.
Yeah,
any
thank
more
you very
questions?
much.
So for Dr. Luna. Okay. There is no more question.
Okay.